and welcome to another video. We're going to be talking about the polynomial factorization theorem. It essentially states that normal polynomial factorization works. For example, if I have the polynomial x squared, say minus 1, this is equal to, of course, x plus 1 times x minus 1. And this theorem tells me that sum a, in this case 1 and minus 1, is a root of the polynomial if and only if x minus the number, so in this case x minus minus 1 and x minus plus 1 are factors of the polynomial. So that's precisely what this says. Formally, we consider some integral domain R and some polynomial over that integral domain, and we have some root a, right? So we want to prove an equivalence, and as such we need to show both implications. So let's begin with the with this implication. Suppose that x minus 1 does divide f. Okay, this means that f is equal to x minus a times g for some g from the ring of polynomials x r, right? Substitution of a for x yields fa is equal to, from up here, a minus a times g of a. Now here of course we have g of x. A minus a times g of a. This naturally is 0 times g of a, and thus it is 0. Ergo, a is a root. So this proves the first implication. Now we shall demonstrate the opposite implication. Right. So let QR be some polynomials over the integral domain R, and let them specifically be the sum, quotient, and remainder after the division of f by x minus a. Now observe that x minus a is a monic polynomial, and as such we don't need a field of fractions. Thus f is equal to x minus a times q plus r. But of course we know that the degree and the existence of such QR that this holds is guaranteed by the previous theorem. We know that the degree of R, that was the polynomial integer division theorem, the degree of R is smaller than the degree of x minus a, but that's of course 1. So the degree of R is 0, and as such it is a constant term. R is a constant term. Okay, that's interesting. Substitution for of a for x yields 0 is equal to f of a, because we assume that a is the root. This is equal to a minus a times q of a plus r of a, by definition of q and r. After the substitution, of course, this is equal to 0 times q of a plus r of a. But r is a constant term, so just r. And this is r, right? In other words, r is 0. And thus, we have f is equal to x minus a times q. And thus, we have x minus a dividing f, which is precisely what we wanted. And this concludes the proof.